Many of the processes in a plant need to be monitored constantly to ensure that they're performing correctly. So vital process variables are normally monitored by process instrumentation. Process instruments provide plant personnel with information that can be used to operate the plant safely and efficiently. For a plant to operate smoothly and efficiently, a number of process variables have to be monitored. Basically, a process variable is a physical condition whose variation can affect the operation of an industrial process. 4 process variables commonly monitored in a plant are pressure, temperature, level, and flow. The job of monitoring process variables is typically handled by process instrumentation. Process instrumentation is a general term used to describe instruments that monitor or control process variables. An instrument is any device used to measure, indicate, control, or transmit information about a process or system. For example, this temperature gauge measures the temperature of a liquid and indicates the temperature by means of a pointer and a scale. This temperature controller is an instrument that controls. It receives a signal from a sensor that measures the temperature of a liquid at a specific point in the process. The controller then compares that temperature to a predetermined value called a set point. If the measured temperature is higher or lower than the set point, the controller transmits a signal to another device which adjusts the temperature until it matches the set point. Plants can have different kinds of instruments providing information about process variables. These instruments may include indicators, gauges, recorders, and digital meters. The information that these instruments provide is valuable only if it's accurate. For that reason, you have to be able to read instruments correctly. Many indicating instruments use a pointer and a scale to indicate a measured value. When there's a gap between the pointer and the scale, an optical illusion called parallax has to be taken into account when the instrument is read. For example, when this pressure gauge is viewed from the right of center, the pointer seems to indicate 29.5 pounds per square inch. But when the gauge is viewed from the left of center, the pointer seems to indicate 30.5 pounds per square inch. When that's done, we can see that the pointer is actually indicating a value of 30 pounds per square inch. Another consideration to keep in mind when reading an instrument is whether or not the instrument has a multiplication factor. Multiplication factors are used so that very large values can be indicated without having to show all of the digits. For example, the pointer on this pressure instrument appears to be indicating about 46 pounds of pressure, but the instrument has a multiplication factor of 10. So the actual pressure reading is 46 times 10, or 460 pounds per square inch. Now, the way an instrument is read will also depend on the type of instrument you're working with. Indicators and gauges both have scales marked off in units of the variable being measured, and they're both read basically in the same manner. We'll use this indicator scale to see how these instruments are read. The major divisions on a scale are often divided into smaller units or subdivisions. The major divisions usually have numbers printed next to them, but subdivisions may not. To determine the value of each subdivision, first choose 2 adjacent major divisions and calculate the difference between their values. On this scale, the difference between 60 and 50 is 10. Next, count the number of subdivisions between the 2 major divisions. In this case, there are 5. Then, divide the difference between the major divisions by the number of subdivisions. 10 divided by 5 is 2, so each subdivision has a value of 2. Now, if the indication of a value falls between 2 subdivision marks, it's usually okay to estimate the reading by selecting a number between the 2 subdivision values. Indicators and gauges both indicate the value of a process variable at the time of the reading. But another instrument, a recorder, indicates the present value of a variable and provides a continuous, permanent record of the value over a given period of time. This particular instrument is called a strip chart recorder. It has a paper chart that moves slowly through the recorder during operation. A pointer at the top of the recorder indicates the present value of the variable being monitored, while a pen marks on the paper chart, creating a graph that shows the value of the variable over a period of time. Some recorders can record the values of several variables at the same time, or the same variable measured at several locations in the plant. They're known as multi-point recorders. Multi-point recorders sometimes use different colors or numbers to help distinguish between the different variables or points. Another instrument that's commonly found in a plant is a digital meter. A digital meter expresses the value of a variable as a series of numbers. The numbers on a digital meter can be lighted electronically, or they can be on a mechanically rotated set of numbered wheels. In this topic, we described what process variables and process instrumentation are, and we talked about how to read several basic types of instruments. Now let's try some practice questions that relate to this material. The job of monitoring process variables is typically handled by process instrumentation. Process instrumentation is a general term used to describe instruments that monitor or control process variables. Another consideration to keep in mind when reading an instrument is whether or not the instrument has a multiplication factor. Multiplication factors are used so that very large values can be indicated without having to show all of the digits. For example, the pointer on this pressure instrument appears to be indicating about 46 pounds of pressure, but the instrument has a multiplication factor of 10. So the actual pressure reading is 46 times 10, or 460 pounds per square inch. Pressure measurements are widely used in process operations, but the way the measurements are made and the way they're expressed can vary according to the process or material involved. For that reason, you need to understand what pressure is and be familiar with the scales commonly associated with pressure measurement. Simply put, pressure is the amount of force that's applied to a unit of area. For example, the pressure exerted by a solid object is its weight applied over the surface area that it's resting on. If the object weighs 1 pound and the surface area is 1 square inch, then the pressure exerted by the object is 1 pound per square inch, or 1 psi. Of course, not all pressure measurements deal with solid objects. Many deal with liquids. The pressure exerted by a contained liquid is known as hydrostatic pressure, and it's determined by the height or depth of the liquid. Hydrostatic pressure increases as the depth of the liquid increases. This is due to the weight of the liquid pushing down from above. Pressure measurements can also be taken for gases. The pressure exerted by a contained gas is a result of collisions between the molecules of the gas and the walls of the container. The way that atmospheric pressure is taken into account depends on the scale used to measure the pressure. 3 scales commonly used for pressure measurements are the absolute pressure scale, the gauge pressure scale, and the vacuum scale. The absolute scale begins at theoretical zero pressure, a condition of no pressure and a total absence of air. On the absolute scale, atmospheric pressure is 14.7 pounds per square inch absolute, or psia. But absolute pressure isn't always expressed in psia. For example, this instrument indicates absolute pressure in millimeters of mercury. Millimeters of mercury refers to the height of a vertical column of mercury that a given pressure will support. For instance, atmospheric pressure of 14.7 psia will support a vertical column of mercury that's about 760 millimeters in height. Another type of pressure scale is the gauge pressure scale. The gauge scale starts at atmospheric pressure rather than at theoretical zero pressure. Since atmospheric pressure serves as the starting point, it's given a value of 0 on the gauge scale. On an instrument that uses the gauge scale, pressure is indicated in pounds per square inch gauge, or PSIG. But sometimes gauge scale values are expressed simply as PSI. The third pressure scale is the vacuum scale. Vacuum is pressure below atmospheric pressure. Like the gauge scale, the vacuum scale uses atmospheric pressure as its starting point, but the vacuum scale moves toward theoretical zero pressure. The closer it gets to theoretical zero pressure, the greater its value. On vacuum gauges, vacuum is often indicated in inches of mercury. This refers to the level of mercury in a vertical column measured downward from a level representing atmospheric pressure. In other words, if the level of mercury is 8 inches below the level representing atmospheric pressure, then the amount of vacuum is 8 inches of mercury, sometimes abbreviated inches Hg. If theoretical zero pressure, or a condition of perfect vacuum, could be reached, it would have a value of approximately 30 inches of mercury vacuum. A number of different devices can be used to measure pressure. One of the most basic pressure measuring devices is a manometer. A manometer operates on the principle that a column of liquid of a certain height will always exert a specific amount of pressure. One common type of manometer is a U-tube manometer. It consists basically of a U-shaped tube that contains a liquid, and a scale that's located between the two columns or legs of the tube. This scale is marked off in inches of water, a unit commonly used to measure small pressures. When a U-tube manometer is used, changes in pressure are indicated by changes in the heights of the columns of liquid. As long as both ends of the U-tube are exposed to the same pressure, the level of liquid remains at the zero mark. But when more pressure is applied to one leg of the tube, the liquid in that leg is forced downward, while the liquid in the other leg rises by the same amount. The pressure being applied to the manometer is determined by adding the travel in the two legs. In this example, the liquid in one leg is 6 inches below zero, and the liquid in the other leg is 6 inches above zero. So the pressure being applied is 12 inches of water. Now, two other types of manometers that are used in industry are the well manometer and the inclined manometer. Both of these manometers work on the same basic principle as a U-tube manometer, but they're read differently. Rather than adding the levels in two legs, both a well manometer and an inclined manometer are read directly from the top of a single column of liquid. With any type of manometer, the level of the liquid is what indicates the pressure. Different liquids can be used in manometers, and some liquids are read differently than others. So, to get an accurate pressure reading, you have to know how to read the liquid level correctly. The free surface of a column of liquid forms what is known as a meniscus. For example, water and oil both form a concave meniscus, which means that the center of the column is lower than the outer edges. The level of any meniscus should be read at its center, so the level of a concave meniscus is read at the lowest point. Mercury, on the other hand, forms a convex meniscus, which means that the center of the column is higher than the outer edges. So the level of a convex meniscus is read at the highest point. Many of the instruments used to measure pressure contain devices called pressure elements. Basically, pressure elements sense changes in pressure and convert those changes to mechanical motion. Three of the most common pressure elements are board-on tubes, bellows, and diaphragms. This is a C-type board-on tube named for its shape. One end of the board-on tube is attached to the pressure source, while the other end of the tube is closed. When pressure is applied to the tube tries to straighten out. The closed end of the tube moves in proportion to the amount of pressure applied. A mechanical linkage converts the movement of the tube to pointer travel. Another type of pressure element that operates in a manner that's similar to a board-on tube is a bellows. In the arrangement shown here, one end of the bellows is closed. The other end is connected to the pressure source. When pressure is applied, the bellows expands. As the closed end moves, it also moves a mechanical linkage which converts the movement to pointer travel. When the pressure is removed, the bellows contracts and returns to its original position. Another type of pressure element is a diaphragm, or diaphragm capsule. Diaphragms are designed to measure very small changes in pressure. This metallic diaphragm capsule has two pieces of thin metal sealed together to form a capsule. The pressure connection is here. When pressure is applied to the capsule bulges and moves the pointer through a mechanical linkage. Pressure elements such as board-on tubes, bellows, and diaphragms all convert applied pressure to mechanical motion. That mechanical motion is often transferred directly to a pointer mechanism, which indicates changes in pressure on some type of scale. But sometimes, pressure indications need to be sent to other devices in remote locations, such as a recorder located in a control room. One device that's used for this purpose is a pressure transmitter. Here's a simplified illustration of a pressure transmitter that's installed on the side of a tank containing a liquid. A diaphragm pressure element is mounted onto the tank and connected through a mechanical linkage to the transmitter. The transmitter, in turn, is connected to a recorder. We've included the recorder in this drawing, but it's actually located some distance away. During operation, the liquid in the tank exerts pressure on the diaphragm, causing it to bulge. The movement of the diaphragm is transferred by the mechanical linkage to the pressure transmitter. The transmitter then transmits a proportional signal representing the pressure in the tank to the recorder, which provides the pressure indication. In this topic, we described what pressure is, and we looked at the scales normally used to express pressure measurements. We also looked at several types of pressure measuring devices. Now let's try some practice questions. 3 scales commonly used for pressure measurements are the absolute pressure scale, the gauge pressure scale, and the vacuum scale. The absolute scale begins at theoretical zero pressure, a condition of no pressure and a total absence of air. A number of different devices can be used to measure pressure. One of the most basic pressure measuring devices is a manometer. A manometer operates on the principle that a column of liquid of a certain height will always exert a specific amount of pressure. One common type of manometer is a U-tube manometer. Another type of pressure element is a diaphragm, or diaphragm capsule. Diaphragms are designed to measure very small changes in pressure. This metallic diaphragm capsule has 2 pieces of thin metal sealed together to form a capsule. The pressure connection is here. When pressure is applied to the capsule bulges and moves the pointer through a mechanical linkage. Temperature is a key process variable, and it needs to be measured accurately to help prevent undesirable conditions from occurring in a process. To understand temperature measurement, it helps to have an understanding of what heat and temperature are. Heat is a form of energy, and it's sometimes referred to as thermal energy. Temperature can be thought of as the degree or intensity of heat in a substance. When the temperature of a substance needs to be determined, temperature measuring devices such as this gauge or this thermometer are used. Temperature measuring devices normally have temperature scales. While there are several scales in use today, 2 that are commonly used are the Fahrenheit scale and the Celsius scale. This particular thermometer has both. On the Fahrenheit scale, water freezes at 32 degrees and boils at 212 degrees. On the Celsius scale, water freezes at 0 degrees and boils at 100 degrees. A thermometer is a basic temperature measuring instrument that's often used in industry. One common type of thermometer is the fluid or liquid in glass thermometer. Fluid thermometers work on the principle that most fluids expand when they're heated and contract when they're cooled. The fluid responds to increases in temperature by moving up a capillary tube. It responds to decreases in temperature by moving down the tube. Temperature is indicated by the scale, which is usually either etched onto the tube or attached to the tube. Another common type of thermometer is a bimetallic thermometer. Bimetallic thermometers are ideal for many industrial applications because they are very rugged. Bimetallic thermometers operate on the principle that metals, like liquids, expand when they're heated and contract when they're cooled. A bimetallic thermometer has a bimetallic element, which is a strip that's made of 2 different metals and formed into a coil. An increase in temperature will cause the metals to expand at different rates. The unequal expansion causes the element to rotate slightly. The rotation turns a rod, which in turn moves a pointer. The pointer movement indicates the change in temperature. If the temperature decreases, the opposite effect occurs. One thing to keep in mind about using fluid thermometers or bimetallic thermometers is to not overheat them. Overheating or overranging a thermometer can damage it. While many temperature indicators are mechanical devices, some, like this thermocouple, are thermoelectric devices. They convert heat into electricity to measure temperature. A thermocouple consists of 2 wires of different metals joined at one end. The opposite ends of the wires are connected to an electronic circuit, which in turn is connected to an indicator. When heat is applied to the joined ends, a small voltage is generated in the wires. The electronic circuit detects the voltage and converts it to a corresponding temperature indication. Another thermoelectric device is a resistance temperature detector, or RTD. An RTD is a resistor whose electrical resistance changes with temperature. The resistor is connected to an electronic circuit, which is connected to an indicator. As the temperature changes, so does the resistance of the RTD. This causes a change in the amount of current flowing through the resistor. The electronic circuit detects this current change and converts it to a corresponding temperature reading. In this topic, we talked about heat and temperature, and we identified scales often used for temperature measurement. We also saw some common temperature measuring devices, including thermometers, a thermocouple, and an RTD. Now let's try some practice questions. To understand temperature measurement, it helps to have an understanding of what heat and temperature are. Heat is a form of energy, and it's sometimes referred to as thermal energy. Temperature can be thought of as the degree or intensity of heat in a substance. Fluid thermometers work on the principle that most fluids expand when they're heated and contract when they're cooled. The fluid responds to increases in temperature by moving up a capillary tube. It responds to decreases in temperature by moving down the tube. An RTD is a resistor whose electrical resistance changes with temperature. The resistor is connected to an electronic circuit, which is connected to an indicator. As the temperature changes, so does the resistance of the RTD. This causes a change in the amount of current flowing through the resistor. The electronic circuit detects this current change and converts it to a corresponding temperature reading.